Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks, section 10.1. This is titled The Sum and Product Rules. We're getting into this introduction to counting. Chapter 10 is all about counting numbers of possibilities, numbers of objects. And in this first section, we're introduced to a couple basic rules, right? These sum and product rules. All right. So counting, as simple as it may seem initially, is a central topic in discrete mathematics. Most children begin their education in mathematics by learning to count, one, then two, and so forth. We're not counting that way, obviously. In discrete mathematics, the goal is to count the number of elements in, or the cardinality of, a finite set. We've talked about cardinality of sets before, right? Given a description of the set. Determining a set's cardinality often requires exploiting some mathematical structure of the set. So they go through this example first here where it says a bakery sells 6 different varieties of cupcakes: chocolate, vanilla, red velvet, etc. The question is, how many ways are there to fill a box with 24 cupcakes from the 6 varieties? The order in which the cupcakes are selected is unimportant. Right? All that matters is the number of each variety in the box after they are chosen. The answer to this cupcake counting problem is 118,755, too much to count by hand. Now, we're actually going to figure out how to do this kind of a problem, throughout this chapter. We just don't know yet. We haven't seen the method, the procedure, how I would work it yet. All right. So this material will cover a systematic technique to derive that number, right, for the cupcake counting question. While counting cupcake selections may not seem like a compelling application, the same techniques can be used to count the number of ways 24 identical tasks can be assigned to a network of 6 processors, which in turn can be used to calculate the probability that a random assignment distributes the workload evenly among the 6 processors and whatever. Right? Basically all they're saying here is that there are more important applications of what you're going to be learning in this chapter. Counting is an important mathematical tool to analyze many problems that arise in computer science. Counting is useful, for example, to understand the amount of a particular resource used in a computer system or computation. Counting is also used to determine the number of valid passwords for a security system or addresses in a network to ensure that there are enough unique choices to meet the demand. Counting is also at the heart of discrete probability, which is central to many areas of science. All right, so there's your intro. All right, so the first rule we're learning about is the product rule. And hopefully you recall from an earlier chapter on sets, I believe it was chapter 3, the Cartesian product of some sets was just a set of ordered pairs or ordered triples or ordered quadruples or whatever, ordered n tuples. And remember, the cardinality of a Cartesian product was the product of the cardinalities of each set. Right? So that's what we're getting into here. All right, so the two most basic rules of counting are the sum rule and the product rule. These two rules, applied in different combinations, can be used to handle a wide range of counting problems. All right. The product rule provides a way to count sequences. While sequences may not seem like a particularly common type of object to count, many sets can be expressed as a set of sequences. So here's the product rule. And again, you've seen this back in the section on Cartesian products. So suppose A1, A2, all the way up to AN are finite sets. Then the cardinality of their Cartesian product, A1 cross A2 cross A3, all the way up to cross AN, is the product of the cardinalities of each set. The cardinality of A1 times the cardinality of A2 times ... times the cardinality of AN. And again, you have seen this before. So they go through an example here where they say, hey, consider a restaurant that has a breakfast special that includes a drink, a main course, and a side. And then the set of choices for each category are the following. So we have these sets. Set D is the set of drinks, which is just made up of coffee and orange juice. So the cardinality of D is 2. Set M is the set of main courses that you can choose from, pancakes or eggs. So the cardinality of M is also just 2. And S is the set of sides, right? Bacon, sausage, hash browns. The cardinality of S is 3. So any particular breakfast selection can be described as a triplet, right? An ordered triple, with your choice of drink in the first component, comma, main course in the second component, comma, and a side in the third component. For example, this ordered triple, coffee, comma, pancakes, comma, bacon, this is one particular breakfast combination. The set of all possible choices is the same as the set of all these triples or sequences, where the first entry is a drink, the second entry is a main course, and the third entry is a side. So what does that remind you of? That is the Cartesian product of those three sets, the drink set, main course set, and side set. So the cardinality of this Cartesian product, this is all the breakfast choices, is equal to the product of the cardinalities of each set, 2 times 2 times 3, or 12. There'd be 12 possible breakfast combinations, if you could only choose one of each. All right, so right now we're only working with the if you can only choose one from each set, then there'd be 12 breakfast combos. And they show you all 12 here. Right, and you can play the animation and stuff, but see, they show you all the elements of the Cartesian product of D and M and S, D cross M cross S. They show you all 12 of these ordered triples. Alright, so what we're given in this activity is something similar, but instead of drinks and main courses and sides, we have so a burrito stand sells burritos with different choices of stuffing. The set of choices for each category are, filling, the filling set, chicken, beef, or pork, so 3 elements in that. The bean set, black or pinto, 2 elements in that. And the salsa set, with mild, medium, or hot, 3 elements in that. So if every burrito has a filling, beans, and salsa, so again, only one from each. All right, right now we're sticking to you can only choose one thing from each set. In a later section, we'll talk about, well, what if you could choose 2 things from one set? All right, so we'll get to that kind of stuff later, but this is just an introduction to a pretty basic rule, the product rule, where again we're only picking one thing. So like chicken, black beans, mild sauce is one option, or chicken, black beans, medium salsa, that's 2. And chicken black hot, that's 3. Beef black mild, beef black medium, beef black. You could count them all if you wanted without doing this product rule, but that would get kind of tedious, especially if these were larger sets. All right, so if every burrito has a filling, beans, and salsa, how many possible burrito combinations are there? Well, again, that would just be the size of the Cartesian product of these 3 sets, F cross B cross S, let's say. So 3 times 2 times 3, 18. There'd be 18 different, burrito combos that could be made. All right. Now, suppose that the customer can also now select grilled veggies as a filling. All right, so now I have chicken, beef, pork, and grilled veggies. So that just changes the cardinality of the filling set to 4 instead of 3. How many selections are there now, right, with a filling, beans, and salsa? 4 times 2 times 3 would be 24. There'd be 24 different ordered triples that we could make. All right, now suppose that the burrito stand introduces a choice between plain flour or whole wheat tortillas. The additional option to select veggies as a filling is still available as well. Well, this adds another set. This adds another set. So now instead of fillings, beans, and salsa set, we now have tortilla set. And the tortilla set would have white or wheat, plain flour or whole wheat. So we'd have this tortilla set as well, and now our choices would be ordered quadruples: a tortilla, a filling, a bean, a salsa. So you'd have 2 times 4, because again, they got the veggies. 2 times 4 times 2 times 3. Or just 2 times the previous choice. There'd be 48 different burrito combos that we could make. See, they added this tortilla set. Now, again, be careful. This is only for if you're allowed to select one from each set. If you're allowed to select one thing from each set. Okay. Now this concept here, what we went through with the breakfast choices, burrito choices, is very similar to what we're going to see here with counting strings. This product rule will still come into play. So suppose, again, sigma here, this fancy sigma, is a set of characters called an alphabet. Then sigma to the nth, that would be the Cartesian product of sigma with itself n times, is the set of all strings of length n whose characters come from the alphabet. For example, if the alphabet is made up of just 0 and 1, then sigma to the 6th here is the set of all strings with zeros and ones of length 6 bits, binary strings with 6 bits. The strings XXY ZX and ZYY ZX ZY are examples of the strings in the set XYZ to the 5th, right? Your alphabet is X, Y, and Z, and you got 5 of them, the length of 5. The product rule can be applied directly to determine the number of strings given a length. Okay, so same product rule. Alright, so here I'm going to pull up a piece of paper on the side. Alright, and hopefully I write big enough where you can read it. We're asked how many 6-bit strings are there. Now this is bits, bytes, right? We're only using, we're talking about binary when they say bit. So like the alphabet here is just zeros and ones. And we're talking about, 6-bit strings. So this set here, right? 0, 1 to the 6th. Now the cardinality of this set, right, this is 0, 1 cross 0, 1 cross 0, 1 cross 0, 1. Remember using the product rule, right? Well, you just take the cardinality of each set and multiply them, right? Each of these sets has a cardinality of 2, and there's 6 of them. All right, so 2 to the 6th power, that's 64. There are 64 6-bit strings. Right. Okay. Now they give us certain conditions. Now, how many 6-bit strings are there that begin with 0, 1? So instead of 0, 1 to the 6th, we have, it has to start with 0. So the first entry in the 6th tuple, or the first entry in the string, has to be just 0. Cross. And then the second entry in the 6th tuple, or the second entry in the string, has to be a 1. And then the rest of them can be 0 or 1. So I'd have 0 or 1, but then, for the last 4. Right? So this is how we'd construct a string that they're talking about there, right? 0 has to be in the first spot, 1 has to be in the second spot, and then the other ones can be either 0 or 1. So the cardinality of this set, and applying the product rule, would just be 1 times 1, right? The cardinality of these two, times 2 to the 4th. Or, 16. There'd only be 16 strings, bit strings, that start with 0 and 1 and have a length of 6. Again, more conditions. Now this is a different set. This is in bits. How many strings of length 4 are over the alphabet ABC? So here we're talking about here's the alphabet. We're choosing from values ABC, and we're making bit strings of length 4. Or you could talk about quadruples, right? 4 tuples, and either one of them can be A, B, or C. So we're talking about this ABC to the 4th, and the cardinality of this, right? How many of these are there? Well, that would be 3 to the 4th. Right? Each one of the sets has a length, a cardinality of 3. So there'd be 81 of those, right? AAA, AAB, AAC, blah 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 blah. Right? You count off 81 of those. Or I'm sorry, length 4. AAAA, AAAB, AAAC. Right? There'd be 81 of those. And finally, how many strings of length 4 are there with this alphabet, using A's, B's, and C's, that end with the character C? So the first 2 can be either A, B, or C, right? So just the first 3. So again, the first 3 can either be A, B, or C. The last one has to be a C, right? And then we're doing the cardinality of this set. And again, using the product rule here, this is one big Cartesian product. It'd be 3 to the 3rd times 1, or just 3 to the 3rd. Right? So 27 of these strings of length 4 with A, B's, and C's would have C at the end. Right? So again, just pay attention to the restrictions. Right? Okay, so hopefully that all made some sense. All right, so that was the product rule. Next we have another pretty basic rule, and we'll get into a much more generalized version of this rule in a later section. But for right now, we're doing a pretty simple beginning version of this sum rule. So in that breakfast example earlier, right, the product rule was applied because the customer selects a drink and a main course and a side. And will usually imply multiplication, product. In contrast, the sum rule is applied when there are multiple choices but only one selection is made. For example, suppose a customer just orders a drink. The customer selects a hot drink or a cold drink. See the word or here. Usually the word or will imply that there's some sort of sum going on in the counting. And the word and, like you saw here, a drink and a main course and a side, will imply usually there's some sort of multiplication going on in the counting. So if the customer just orders a drink, the customer selects a hot or a cold drink. The hot drink selections are, coffee, hot cocoa, tea. The cold drink selections are milk and orange juice. The total number of choices is 5, right? 3 plus 2. Because you either choose one or the other. A coffee, hot cocoa, tea. Or if they chose a cold drink, they have the milk, orange juice, giving me a total of 5 possibilities. So you see there's a sum going on there, not a product. It's not 3 times 2, it's 3 plus 2. Total number of choices is 5. Right, 3 hot drink choices plus 2 cold drink choices. So here's a formal statement of the sum rule, again expressed in terms of sets. Now this is in terms of unions. Remember, union was a symbol for or. Now, like I said, this is a very basic version of this rule. We're going to see a much more generalized version of the sum rule called the inclusion-exclusion principle in a later section. But for right now, we're going to consider, n sets, A1 through AN. Now, big if here. If the sets are mutually disjoint, you've seen these words before when we talked about partitions. if all the set, that means none of the sets have any overlap. None of these sets share anything with each other. Right? You take any two of them, their intersection is empty. That's what mutually disjoint means. Then, the cardinality of the union of all these sets is going to be the sum of each cardinality, which is why back in this hot drink, cold drink thing, you could just add them up, right? If I could choose one drink, and I had 3 hot choices, 2 cold choices, that'd be 5 total. Notice that the hot drink set and the cold drink set had nothing in common. They were disjoint. Right, so the sets have to be mutually disjoint in order for you to apply this rule. Alright, so they did the cold drink, hot drink thing like I just said. Alright, now we can combine rules, of course. Right, just because I'm looking at the sum rule now doesn't mean the product rule doesn't come into play ever. So here's an example where they say, hey, consider counting passwords here. Consider a system in which a password must be a string of length between 6 and 8. So that means 6, 7, or 8. The characters can be any lowercase letter or digit. So you see L, suppose L is the set of all lowercase letters, and D is the set of digits. The cardinality of L is 26, right? There are 26 letters in the English alphabet. And the cardinality of D is 10, there are 10 digits. The set of all allowed characters, which they're calling C here, is just L union D, right? The union of those two. And those are disjoint, right? None of the letters are digits and none of the digits are letters. So the number of characters allowed is 26 plus 10, 36. Alright, so there they applied the sum rule. Now they're saying, suppose A sub j denotes the strings of length j over alphabet C, right, the letters and digits. By the product rule, the cardinality of AJ is 36 to the jth power, right? Because you'd have, for all j choices, you'd have, for all j spots, you'd have 36 choices, and 36 times 36, 36 to the jth power. So notice that for j not equal to k, aj and ak are disjoint, because you can't have a password of length j equal to j and equal to k at the same time. So if the user must select a password of length 6, 7, or 8, notice the ORs. Now we're getting back to the sum rule again. The number of passwords of length 6 in union with the number of passwords of length 7 in union with the number of passwords of length 8, it'd be or. Just add them up, 36 to the 6 plus 36 to the 7 plus 36 to the 8, a huge number. Right, so again, we can combine the rules throughout an example. Alright, so I'll let you look at this one on your own. Alright, the people choosing laptops, you got a choice of, alright, maybe I'll go through it. You're counting laptop selections. You choose a screen size, you got 3 choices there. Then a processor speed, you got 2 choices there. And then for the choice of storage, so you can either do a solid state or hard disk. See, it's an OR. And the solid state choices you have 3. The hard disk choices you have 2. So or that you have 5 choices then for storage. Right? It's 3 plus 2. So 3, and then for the total, when you're making the laptops all together, there's 3 choices for screen, 2 choices for processor, and then again 5 choices for storage. 3 times 2 times 5 would be 30. That's a nice little combination of where you're using the sum rule in some cases with the OR, and then the product rule with AND. Alright, so this is about it. So let me go through this here on some paper. So I'll bring the paper up on the screen. Hopefully you can see it. Alright, well, right now it's just a part of my desk. Alright, there's a piece of paper. Alright, and we're asked to, look at, a bit string consists of zeros and ones, as we know. And this is a bit string of 4 bits. Alright, cool. how many 6-bit strings are there that begin and end with a 1 or start with 0, 0? So let me do this. I'm going to have A be the set of 6-bit strings beginning and ending with a 1. And let's count up the cardinality of this set. Alright, now the cardinality of this set, remember, would be like like I did earlier. The first bit has to be the number 1. We're doing a Cartesian product here. When we create a string, it's like creating a 6 tuple. Right? You're taking or creating a sequence. So you're forming elements of a Cartesian product. The first element has to be a 1. But then the middle 4 elements can be either 0 or 1. So that's for the middle 4 elements. And then the last element has to be a 1. So just a set with the 1. So the cardinality of this set A, right, this set of all the bit strings, 6-bit strings, beginning and ending with 1, and the middle 4 can be whatever you want, would just be 2 to the 4th, wouldn't it? Because it'd be 1 times 2 to the 4th times 1, so 2 to the 4th, right, which is 16. All right, then they talked about this other kind of set, other kind of string. So I'm going to have set B be the set of strings, set of 6-bit strings that start with 0, 0. All right. Now the cardinality of B, again, the first 2 sets have to have, the first 2 parts of the Cartesian, the first 2 parts of the sequence part of the string have to be 0, and there are 2 of them. And then the last 4 can be either 0 or 1. So this would just be 1 squared, or 1 times, 2 to the 4th again. So there are 16 of those as well. Now, these 2 sets are disjoint, right? A intersect B is empty, right? Has nothing. They have nothing in common, because you can't have a string start with 0, 0 and begin and end with a 1 at the same time. Because if it begins with 1, it's not going to begin with 0, 0. So the number of strings they're talking about, right? They say how many strings, 6-bit strings, begin and end with 1 or start with 0, 0. That'd be the cardinality of A union B, right? And it's an OR, right? So we're using this sum rule. Now again, since they're disjoint, by the sum rule, this will just be the cardinality of A plus the cardinality of B. Right? And we found those both already separately, right? Those are 16 and 16, so 32. There are 32 6-bit strings that either begin and end with 1 or start with 0, 0. So I'm going to put 32 in there. Okay. And then they describe what basically the same thing I did. Now here, how many strings of length 5 or 6 start with a 1? So I'll do something similar. And I'll do something kind of like in the description earlier, in the example earlier. I'm going to have A5 here, A sub 5. This will be the number of 6-bit strings, or sorry, the set of the set of 6-bit strings of length 5 that start with a 1. Starting with 1. Now I hope it's obvious what the cardinality of this set is, A5, what I'm calling A5. You know, it has to start with a 1, right? So there's one choice there. And then the other 4, right, because it's length 5, the other 4 can be either 0 or 1. So you'd have 2 to the 4th. Again, right, it would be 2 to the 4th or 16. Then I'll call A6 the set of 6-bit strings of length 6. Oops, sorry. Why did I say 6-bit strings here of length 5? I should have said 5-bit strings. I am so sorry. That made no sense. This is the set of 5-bit strings starting with 1, A5. My apologies. And here's the set of 6-bit strings starting with 1. And the cardinality of this A6 would be, you know, again, that it has to start with 1. So there's only one choice for the first slot. And then for the other 5, there's 2 choices. So this would be 2 to the 5th using the product rule, right? 32. Now, these two sets, A5 and A6, are disjoint. Oh, sorry, that's bad. If you take their intersection, it'd be empty, because you can't have a string of length 5 also be a string of length 6. Right? These are sets of strings of totally different lengths, so they're not going to have any strings in common. So then, by the sum rule, you know, the cardinality of A5 union A6, right? This strings of length 5 that start with a 1, or start with strings of length 6 that start with a 1, would just be the sum of their cardinalities, 16 plus 32. Wow, I made all sorts of mistakes on this one. I am sorry. 16 plus 32, 2 to the 5th is 32. And that'd be 48. Right? So there'd be 48 strings of either length 5 or length 6 that start with a 1. Right? And these are bit strings, right? So 48. Wonderful. All right, so pull that off, and then your challenge activity is to be counting. Right. There's 5 of these. And I'll do a couple. So just pay attention to what the alphabet is, what you're allowed to use for your password. Right. So it says here each character in a password is either a digit. Right, there's 10 of those, or a lowercase letter. There's 26 of those. So you have 36 choices for a character. How many valid passwords are there with the given restrictions? So length 15, that's just product rule, 36 to the 15th power. And you're asked to enter it with these powers and stuff, right? That's it, right? Because you have 36 choices for each of the 15 slots, each of the 15 characters. So that one was easy, not too much. Now length 20 or 17, same 36 choices you have for the characters. So length 20 would be 36 to the 20th power, right? You have 36 choices for each, or right, plus length 17, 36 to the 17th. Right, the 36 to the 20th is how many passwords of length 20 there are. 36 to the 17th is how many passwords of length 17 there are. And those two sets are disjoint, right? You can't have a password that's both 20 characters long and 17 characters long. So then I can use, when I see the word or here, the sum rule. And I'll do one more. Length is 15, and it cannot start with a digit So for that first slot, you'd have 26 choices. 26 for the first character, right? Because it can't start with a digit. But then the remaining 14, right? That's length 15. The remaining 14 characters can be anything. So then you have 36 choices for the remaining 14. So using the product rule, 36 to the 14th power. All right, and then you got the other levels here. Just pay attention to the restrictions. All right, now nor is just kind of or, right? Let's take those away. Length is 9, and it can't start nor end with a digit. So both those things, right? So just make sure when you're talking about choices, the first choice and the last choice can't be digits, but then the 7 in between can be anything. Right? Then length is 15 or 16, and it must start with a digit. So do it for length 15, do it for length 16, starting with a digit, and then add those, right? Because it'd be one or the other. All right, so hopefully those rules are pretty easy to follow. The product rule for counting, again, it's basic introduction here where you're only allowed to select one element from each set in that Cartesian product. And also the sum rule, where again you're only allowed to select one thing from each set, and the sets are mutually disjoint. So some basic introductory rules here: product rule, sum rule. Then you have your exercises. Again, some of these are assigned. I think all of them might be actually on your assignment. Even if they aren't, I would still recommend looking at all of them just to get more exposure to the material, get more practice. And of course, you can look at the solutions, and but I would I say this almost every time, right? Please try to work them out. Figure out what you're doing before you look at the solutions. Right? Because if you're just copying solutions down, you're not going to learn anything. All right, and if you have any questions, of course, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.